Okay.
That would be pretty fast. I could be more interested.
Okay, so recently I had this, we just had this idea of doing a demonstration about restoring an old fork. And you know, this isn't just about this particular fork or this particular brand. What this is more about is just, it's about the communication between members. And having somebody help you out, someone who has skills that you don't have, and you know, people working together in order to get something accomplished. So that's really what this is about. And so there's a lot of skills that happen here. There's a lot of equipment that's needed, but and that's partially why I wanted to do this talk, is that I don't have things like lathes and mills. I have a lot of welding equipment, but that's when Doug comes into this. So let me explain kind of what needed to happen, and then I will explain why Doug needed to help me out here. And by the way, this wasn't just about me and Doug. I had conversations with other members about this same project. So Jack Larson was a huge help in giving some really great suggestions about doing this. Dan Holman was a really great resource of someone who's taken apart really old things before and tried to put them back together. So you know, that's why these meetings are so great. I mean, coming here and eating a sandwich is great, but when you can get information from other members about something that you have no clue about, it's like, it's exactly why I do this, you know. So this is where we're going. About a 1928 JD, and the fork seemed to be in okay shape, but it's 100 years old, and as Doug has said, there's pretty much nothing that's 100 years old that is straight. They are horrible all the time. You think they're great, you look at it, and it looks great. It is not great. You actually start putting measurement tools on it, you start lining things up, they're horrible. So, here's how the fork works. This is the rigid section of the fork, so this, okay, so this is the steering tube that goes to the frame, and then the lugs down here, they go to rocker arms that then go out to this portion of the fork, and then this slider here fits in here, and then there are springs above and below that slider, and then there's also some springs that go between these posts and here. So what it does is it creates, like, it's kind of a spring fork is really what it is, okay? So how it works is that they're always either bent because they're made of pretty thin walled tubing, or they sat and they got water in them, and the bottoms splay out and get broken. So here is an example of why these tubes always need to be replaced in these castings. So you can take a look at them. One of them, somebody's done some like really scary brazing, and the other one is just had some hard life, right? So that's kind of what goes on. The other thing that can also happen with these is that you need to have a cap that screws on the top that contains the spring set. And if those threads are bad, then you can't contain the spring, right? So there's numerous reasons why we might want to replace these. The other thing that can also happen is these castings. Actually, they're not castings. Well, they might be cast. They're not cast iron. I know that they're steel. At any rate, they can be broken and messed up as well. And it is extremely hard to get these out of the tube without bunging the tube up, right? So these were all furnace brazed originally. It was probably hotter than Hades. They brazed it all and then, you know, cooled down, right? So we are not going to be able to get these things apart, okay? So the first thing that I needed to do was come up with this fixture, right? So I know that it is 6 inches here, right? I know what that dimension is. So then I made this this large fixture to hold these, to cradle the tubes in the right place. And I also got that dimension from the width of the casting. Okay, so now that you can make a fixture where your tubes are exactly parallel and also plumb flush, right? You know, so don't do this sort of stuff. Now we need to go about removing the tubes from the casting. Okay, so that's where, and then let me talk about this fixture over here really quick too. This is for the rigid part. I haven't used this particular fixture yet. Actually, another member, Chris Treat, he did a 28 JD and he used this fixture to straighten his fork as well. So this particular one, its set point is the steering tube, and then I have some jacks, some threaded jacks that can move the fork this way. And then once you get that all set, now all of your work can be done from the triple tree out, so you can get that all square, and then you can also work on this side of the spring casting up here, which this one will, you know, my top clamp won't fit on the fork right now. So that's one of the things that I have to address with this. So that's kind of, you know, I built these fixtures to straighten the forks, and then this one was built to install tubes. Okay, so now I need to have the tubes installed. So you just go with a saw or whatever and you chop off your tubes, and at that point you are in it. You are not going back now. You have cut the tubes off, right?
You're screwed.
Yeah, so now you have to have somebody like Doug who's going to help you out. So here's the problem. People say to themselves, well, it was brazed, I'll just heat the brass up and just pull it out. Well, one of the things that Jack Larson brought up and Dan Holman brought up was that if you heat these castings up too much, you can really start to damage the castings, right? This is a fork. This is something that we want to be strong, and we don't want to hurt ourselves as we're riding down the road, right? So, yeah, and you also don't want it to melt, right? So you really need to take these out in a cold fashion, right? Which means machine them out, okay? So I have heard people where they just cut them out and then people get in there with a die grinder and they just start going and going until that would possibly work, but we have Doug Rollert, master machinist here, to help us out. So I say, Doug, can you help me machine the tubes out of this bridge cast? And he said, yes, but I need a fixture in order to hold this casting in, like, really hold it very sturdily onto the mill table. So I said, I can do that. So once we did the chop, then I built this fixture, which it's kind of hard to imagine this, but this bridge casting here, this with these little rods that hold the springs, those springs go into this, and then the fender brace mount onto here. Okay, so now the thing is mounted onto this fixture with the tubes going vertical this way. Now Doug comes in. He needs to bore out the holes, and the other thing Doug also did was make these tubes for me. So this is German 1-inch chromoly tubing, and what Doug needed to do was make a slot, a 1/4-inch slot in the center of the tubing down to that point, and then he also needed to thread 20 threads per inch at the top. Okay, so now I'm going to turn it over to Doug, because this is really where the magic happened, right? So now he's like,
There you go.
now I'm going to let him go on some big equipment.
Like Tom said, the first thing we needed to try to decide was these are actually, I think the original ones are carbon steel, so you know they're really not very sturdy. Any motorcycle of this age has been thrown down the road a few times. You know, you can look at them like Tom said, but the forks are always bent in one fashion or another. And what I always look at are these slots right here on the you can see in these slots right here, if you're looking at a fork, these got the plungers fit inside here, and once these things get bent, they're in a bind like that, and when that thing goes up and down, it'll start wallering out this hole right here. It's a 1/4 inch slot. Most of them you see are like 3/8 of an inch because things have been bent and so on. So we talked about what kind of tubing to use, so we decided to use chrome moly. Like he said, it's 4130. Chrome moly is, in compared to mild steel, it's much stronger, it's much lighter in weight, and more importantly, it does resist vibration. So they use a lot of that stuff. And what's that?
Is it harder to machine than your regular?
It is, because it's got chromium and molybdenum both in it, so it's a little bit tougher. It does machine okay, but it's a little bit tougher to do. So, on my lathe, I have a collet holder. Does everybody know what that is? You've seen collets before. Collets are ground so that when you use your collet holder and you tighten it down, it puts that particular piece of tubing on dead center. So you know you're centered up on it. And if you ever want to make one of these forks or so on, I used to buy this chrome moly down at Air Parts. Does everybody know where that is on Merriam Lane? So you can buy, they sell a lot of aircraft stuff, but they have every dimension of chrome moly tubing, different thicknesses, wall thickness, and they actually sell it by the foot. It's more expensive to buy it by the foot, but at least you can get it. So a lot of places, they want you to buy a 20-foot piece or so on, So anyway, I have collets on my lathe. They start at like 1/16 of an inch, they go up to 1/8", and they're on by 64ths of an inch. So that's the first thing. So when Tom brought that over, before we got started on this, I could make some accurate dimensions on the length for this particular tubing. So when I got the piece of tubing, of course it's double length. So I have a cutoff tool for my lathe right here. So I made the measurement on that, and then I could cut the tube off like an extra 1/8 of an inch longer. So this is the cutoff tool that I use. It goes in, cuts it off. It's not super accurate, so I make it an 1/8 of an inch longer so I can take a tool and go in and face it off. So now I know that tubing it's going to be completely straight, and the end of it will be parallel and perpendicular. So when I make the measurement, in other words, you're trying to make this stuff meet up in these castings, so it needs to be good and square. So then I could measure off that and make the final face on this end of it right here. So I know I've got the tubing exactly the right length. Then the next thing I had to do was try to figure out the threads per inch on this. So Tom came up with these caps. The guy reproduces these, and these are 20 threads per inch. So if you look at a regular 1-inch thread on parts, so we have national coarse and national fine threads. That's 8 threads per inch and 12 threads per inch. So this is going to be something special. So the way I measure those threads, I don't know if you guys have ever used, or you've probably all got one of these, but this is a screw pitch gauge. So it's got these little feet on it here, and you can go in and pick out the proper one, and this ended up being 20 threads per inch, so I know that. The problem with that is it's going to be a non-standard thread. So American threads, they're at 60-degree pitch on the thread. So this is my thread holder right here, and they on each one of the threads, depending upon whatever pitch it is, there's a depth that when you're machining it, there's a depth that this tool goes into the part. And they put it in a machinist handbook. They put it in and recognize it as a double depth, they call it, because when you're going in and cutting threads, you're cutting on one side, but the piece is going round. So when it goes round, you have to take that double depth that they give you and divide it by 2 to get the proper depth. Now, there's different ways. I have I have this particular tool right here. I can take any American thread per inch, anything 14, 18, 20, and it tells me the double depth. I can pass these tools around if you want to see it. And you have to take that, when you set your lathe up, you got to take that and divide it by 2 so that you get the proper depth. Now that just gets you close. So I have problems with some of these threaded things that these guys make. I don't know where they get their taps sometimes, you know, they're foreign taps, they're all over the place. So what I have to do is come close on my dimension, and then I've got to go in there and kind of sneak up on it to make sure that you get the proper thread. When you set your tool up on the lathe, I have what I call, this is what they call a fishtail gauge. So when you put your threading tool, when you put that in your compound, you lay this piece flat up against your part where you're going, and then you adjust your compound right here so your thread goes into this V right here. And that makes sure that your tool's in the proper position to when you start cutting the threads on it. So there's different ways of doing that. All those dimensions they're all inside of this machinist handbook. The thing I use probably the most, I've got this what we call a Dirk's gauge. It tells you all the information that I need to know, that I use a lot, is in this gauge, this particular little gauge dial. So it's easy to access. Otherwise, you got to look it up through the book. Okay, so once I get that and I set my lathe up, once you set your lathe up, then I've got to set up my feed and my speed and my threads per inch on it. And like I said, the reproduction parts I get, they're all over the place. So there's really 3 different classifications of threads, you know, from tight to regular, like that you get from the store would be kind of medium, and then you can have some that are really loose. So that's why I got to sneak up on those dimensions, because I never know when I get it, whether their tap was dull or whether it was a foreign made thing or what, you know. So anyway, these particular pieces right here, I use as a gauge. I also I've got a whole set of, I can pass these around. These are called ring gauges. These are for standard dimensions. So this would be in the middle of the 3 different thread gauges. So these thread gauges right here are for like standard dimensions, and that's a good thing. But it's a problem when you get like 20 threads per inch, because that's non-standard. So now you're actually going to have to single point those things on the lathe. So anyway, once I get that, on these particular parts right here, I actually ran them on loose, these threads. I kind of ran them loose a little bit, because I know that once I line these up on the milling machine and I go in and cut that groove, that tube's going to come open a little bit. As you can see right here, you're starting at the top and going down through there. And when you cut those threads, as soon as you do that, springs open a little bit, and then your cap won't fit. So if you start out and you put it, you know, really tight, it's not going to fit.
And
So,
you know, to interject really quick, if you you can actually squeeze this together by hand enough to loosen the threads. You can actually feel that the threads will become looser. So the point is, like, if you made it really tight and then it opened up, you could smash it down, but the idea is that we're gonna paint this and we're gonna have really nice brand new paint on it, and the last thing we wanna do is putting a bunch of clamps and stuff on a tube, right? So Doug made it so that assembly after paint is gonna be easier for me by cutting his threads looser on the initial making of the tube.
Yeah, the other thing I have problems with on a lot of the reproduction parts, they make these parts and then they plate them, you know. So then they run their tap in and then they plate them, and then you can't hardly even get them started screwed on there, you know. So a lot of times if I've got a specific tap, I wouldn't have one for 20 threads per inch. I have to run a tap through them just to get the threads, get the plating back out of the thread so you can get them started on it.
That sounds like Chinese spokes.
never seemed to work right.
So you're chasing the threads, how to get that?
Yeah, you gotta chase them just to get them started out. So the next thing I had to do with the tubes there is I take them over to the milling machine. So once I get it on the milling machine, the first thing I do, which this is the standard procedure, I sweep my milling machine. I have a dial indicator like this that I put in, and I sweep my milling machine, the table, because the head on my milling machine is adjustable this way, this way, this way. And you want to make sure when you're doing something like this that your table is parallel and perpendicular to your part, because this is going to get you've got a lot of cumulative dimensions on this thing when you start putting it together, and you have to, you know, the straighter you can get every part, the better it's going to work, and you don't want to be off. So once I do that, I bolt this tube to my table, and then I take an indicator and I put it in the head of my machine, and I run the table back and forth with an indicator, because I want this tube, I don't want it setting, I want it setting perfectly straight on there. Because once you start your mill in the end of this, if this thing's setting cocked, you're gonna be running off on an angle, right? It's not gonna be on center line on the tube.
Yeah, so then the sliders, instead of sliding down like this, the slider will want to do that, and then the fork will bind and not function correctly. So yeah, that's functionally why I had to indicate the table in.
And the other thing that happens is, like on chrome moly, that's pretty tough stuff. So I use a 1/4 inch end mill on it, but I put a block at the end of that tube right there when I'm bolting it down, because I don't want that to start pushing that tube. You know, even with a bunch of clamps on it, you got a lot of pressure when you're putting that on there, especially if I'm feeding it automatically, it'll want to push the tube. So I put a block down on the end of it and bolt it down so the tube can't move. And then the next thing I have to do when I try to find the center of that tube, I don't know if you guys have ever seen an edge finder or not. So this is the tool that you put in your milling machine, and it's kind of spring loaded on the bottom. It's got this little cylinder right here. You straighten it up like that, and you go in against the part, and you keep watching, and as soon as it touches the part, it'll spring off like that. And that way you know you're precisely on the edge of the tube. On the edge of the tubing. So then what you have to do to find center, if you have a 1-inch tube, you have to take half of the diameter of the tube, which would be 1/2 inch, and this is a 1/2 inch. So you add another 1/4 to that. So that moves your tool precisely down the center of the tubing. You see what I mean? Does that make sense to you? So you got a 1-inch tube. You know, halfway across the 1-inch tube is a 1/2 inch. You've got this as a 1/2 inch. Half of that is a 1/4. So I can dial this in on my machine to 3/4 inch, 750. So I move at 750, and now I'm dead nuts in the middle of the tubing, right? And we know the tubing right now is perfectly parallel to the table, okay? So at that point in time, I've got I put like 5 clamps on this tube right here. Because we're trying to hold thousandths of an inch, right? So, you know, nothing can move on this thing. So what I do is, I start I'll put the first clamp maybe 1 inch or so in here, and I start feeding my end mill in the edge of the tube. And as it goes into the edge of the tube right there, and I get to my clamp, I have to stop and move the clamp, because I know you just can't keep taking off clamps, or pretty soon something's going to start moving on you, you know? So it's better to have too many than too few on there. So I use like five clamps on there. That way I go all the way down and cut that. And once I do that, I go back. I actually went back on this and stick this back in the mill, because once you run your end mill on these threads right here, you're going to kind of screw up the threads on the end where the mill goes in. And I use a thread file. I don't know if you guys have ever seen these or not, but anyway, these thread files are different threads per inch. So, for example, that's 20 threads per inch. So I can stick this back in the lathe. I can just hold it on the part with it running, and it'll just go right down the threads. knocks all those burrs off, so the part will go back in there pretty easy. So that's basically what you have to do to make the tubes. It's very important on this, and we'll talk about this here in a minute, but it's really important on this to make sure I take it and I mic this tubing before I start. This tubing is supposed to be 1 inch. You know, it's all over the place. It can be 5 thousandths too big, 2 thousandths too small. And the idea is here, when you get to this casting, which you're going to talk about, you have to have 2 to 5 thousandths clearance in there in order to make sure that when you heat this and you run if you're gonna, I don't know if you brazed it or if you silver soldered that, in order to get the correct action to suck that brass into that part. It makes the strongest joint with 2 to 5 thousandths. If you get more than that, then the joint's gonna be weak. It gets weaker the more clearance you have. And that's actually the problem with just taking a burr tool and going in there. You know, you're not round anymore. So that's not a good thing. And you get a minute, you guys can look at this. But this is kind of tricky because this casting right here, man, that thing out on the edges here, it's super thin. So it's kind of thicker in the middle here. It's kind of tapered, thick and thin. So when I set this up in this machine right here, I'm going to set that on the milling machine right there. I've got to really, I tie this thing down tight on the milling machine. And once I get that on there, then I always go in and I take an indicator because I want to make sure, I mean, you can make a fixture like this. We're talking about 2 to 5 thousandths, you know. It needs to be precision. So once we put this part in here, I take a dial indicator and go into each one of these tubes right here. I want to make sure I run the indicator down inside of this casting right here to make sure that thing is sitting parallel and perpendicular.
So it's,
if it's sitting just a little bit like this or that, when you put that tube in there, it's going to be going this way or that way, so it's got to be dead. So that's the first thing I do after I tie it down. The next thing I got to do, I've got an indicator. It's a longer indicator. I go inside the hole, each one of those holes. It's still got the tube. We just cut the original tubes. We just cut them off. So you got a piece of tubing sticking up like that. So I go inside that tube because I want to find the dead center of this hole. And the problem is, when you try to find the center of a hole and you've got something that's long, you can go in there around just, if you don't indicate it, I'm sorry. You have to indicate it to make sure it's straight up and down to start with. If you don't do that, and you just indicate at the top, and your fixture setting just a little bit this way or that way, you know, you're going to be off. It's not going to be straight. So once I get that established, I'm in the center of the hole on it. Then this is a boring head right here that I stick in my mill, and this boring head right here, I can adjust this in thousandths of an inch. So the idea is then I go into each one of those where the fork tubes go and bore them. I know everything right now because we indicated it all, and everything's parallel and everything's perpendicular, right? And I try to hold 5 thousandths. The first one I did it perfect. The second one I had to haul over to Jackson because that chrome moly's pretty hard stuff. So a lot of times if your tool's not super sharp, you know, when you're trying to take a thousandth of an inch or something, it'll get on the piece of material and just ride on it and it won't cut, you know. So I got in that position on the second set that I did. Took it over to Jackson. He honed it to get it on dimension. I think that's
well, then he has to go and do the other hole.
Yeah.
Right, so you do one, and then you crank the bed over to do the other hole, and you have to do the same thing on the other hole, right?
Right, exactly. And I can't stress enough that how important it is to keep that 2 to 5 thousandths dimension between the casting and the tubing right here, because the more that opens up, the weaker the joint's going to be. So
Yeah,
we need to
so-
hold that, so you get this capillary action, you know, you guys have sweat probably copper tubing before, you know how you put your, you know how you heat it up and it just kind of sucks the solder into it. It'll do the same thing with like silver solder and so on. The more you open that up, it won't pull all the silver solder into the joint, so you don't get a strong joint. So
Yeah, so then, after Doug did all this machine work, make the tubes and machine these out, now we're back into the mode of putting the tubes into the casting. So, all of this stuff is clamped down. This piece here that's in the fixture, this is on here, and it is clamping the bridge casting onto the fixture. The idea here is that I don't want the tubes and I don't want the casting to move, right? So I've got clamps going across the tubes and I've clamped the casting in. The other thing that we have to have in place here is I need to have my lugs in the correct place as well. So there's some indicating that has to happen down there, and this is this basically is the stock inner dimension for a JD form. So I just cut a piece of tubing, welded it to a piece of angle, and I can clamp it to move it around if I need. Okay. The other thing that needs to happen is that now we have to have this slot exactly in the center, right? If I have this slot going up like this, now instead of our sliders moving like this, it's going to be like that, and it will start to bind on the slider. So how I achieved that was I take a piece of 1/4 inch thick plate, which is exactly the dimension that he ran the end mill down, right? And so the center of where this place sits off of the fixture is exactly the center of the tube. Okay, so this goes in. I clamp this in place. I use more than just one little clamp. I got a whole bunch of clamps. Clamp that in place. Now the next thing I'll do is I want, as we were talking about this capillary action, I'm putting this together, not brazing it together. I'm actually using a silver solder, a really high, I think that it's a 56% silver solder, so it's really, really high in silver. It is a pretty hot silver solder, but it is extraordinarily strong. But it doesn't take as much heat as braze. Okay, so the first thing I did is I drilled a few holes in the bridge casting and the tubes down here. So I drilled 1/4 inch holes on the sides of the castings and also on the insides and the outsides of the tubes. So now what I can do is I can go in and I can actually do a little TIG weld, a little plug TIG weld, right? So now I've,
cheating.
yeah, well, so, you know, here's the nice thing about this particular metallurgy that Harley did was this can be welded. This is weldable stuff, you know. If we start dealing with other parts, Indian, for instance, of the same time period, their metallurgy wasn't quite as good as Harley, and some of the stuff had really, really high carbon content. So it's really hard to electrically weld. However, Harley's not that way, and we were able to do this old cheat method. And at this point, we probably don't even need to silver solder it. It's TIG welded in there, right? I've got 2 TIG welds on each side of the lugs here, and I've got a TIG weld there. But I decided to go ahead and silver solder it anyway. The other thing I did is I went with and put some 16th inch holes just to feed a little bit more silver solder into the casting. Okay, so I get this thing super hot with a torch, get it hot until a point where it's starting to sweat. And so then I go all the way around the seam on top and bottom, and then I take my little silver solder rod and I just push it into those weep holes. I must have gotten 1.5 inches, 2 inches of silver solder in each of these joints. So there's a lot of solder in those joints. Then when you're done, let it cool in the fixture. You don't pull it out when it's piping hot. Let everything normalize, and you're finished. So it's a lot of work, but there are places that do this stuff. There's a machinist back east who he makes tubes and he installs all this stuff. So could you send it to the guy? Yes. I've seen his work. It's great. He's amazing. He's done a lot of these forks. But where's the fun in that? I like to restore this stuff. I want to like go to Doug's house and see this stuff go on. I want to like, I don't know, this is the hobby for me. This is the hobby for me, is learning this stuff and having a conversation with people. So yeah, it was way more work than if I just put it in a box and sent it to the guy back east. But I learned a hell of a lot.
I wonder what they charge to do that.
It's like in the $800 or $900 range. So by the time you start to add up all the effort that it took to do this, it might, money-wise, it might have made sense for me to like send it, but that's also not why I do this hobby.
How many hours you got in that, Doug? Machine.
I got a bunch of it. It's just, I probably overkill on what I do just because I want it to come out right, you know. It's so critical. You go to all this work, you don't want to put it all together and have
Especially
a
when it's
lock up.
somebody else's too.
Yeah.
Yeah.
Well,
Yeah, Mike.
the other problem is, I mean, if you screw this up, you're done. You know, if you screw that casting up, there aren't any more castings. You know, you're done. The party's over on that. So I wanted to be real picky on it. I didn't want to go out trying to shop for a 1928 center casting anywhere. You know.
Yeah.
After watching all this and hearing you, this has to be the most labor-intensive piece of a motorcycle to redo or rebuild, even more than building a whole frame with jigs, right?
This is child's play. This is child's play compared to a frame. Yeah, this is nothing. And like all this, and so what's good about this is that, okay, so we learned about a Harley fork today, but these are the same sorts of techniques that you could use on any make and model in your motorcycle. You can make these fixtures to fix your Honda fork or do whatever, right?
Tom's actually done 2 or 3 of these too, because you know, as soon as somebody finds out you can do that, and then they all want somebody to do it for them.
Yeah, Jim.
You think they did it back that same way in the teens and 20s at the factory?
I guarantee they have some sort of a fixture that all this stuff was in.
Oh yeah.
Yeah, but I mean, they probably had huge amounts of BTU. They probably had furnaces going. They probably put everything into a furnace, and then it came out and they just started throwing braze. And if you look at original castings, and people who've redone these bikes will attest to this, that brass is everywhere. That brass is dripping down the sides. It looks like snot's been blown out of, you know, and
They're not really all that accurate either. If you start,
yeah, well, that's actually a good point. On the measurements I took on the original fork, one of these tubes was a 1/16 of an inch further down than the other one. Right? So
out of the factory that way.
out of the factory. Okay? So this is by far more accurate than 1928 Harley. I mean, of course, Harley probably nailed it on most of them. I've got to imagine that's true. But, you know, these original, when you get the paint and the rust off, man, the castings, there's brass everywhere. They don't look so great. I mean, the Indian, the 27 Indian that I did, once I got paint and rust off the frames, they were pretty bad. I mean, it was just, it seemed like they got more brass on the outside of the frame than they did on the inside.
Brass was cheap back then.
Yeah, yeah.
You know, what Harley did, after they braze all that stuff together, they would drill the rocker stud holes after everything else is done.
Oh.
That way, if one's off this way or this way a little bit, the hole's still in the right place.
Well, there you go. That's why 1/16 of an inch didn't matter. Perfect. Excellent.
Close enough for the girls' weekend.
So, anyway, that's the process. At least on this one.
All right, good job.
Yeah.
Yeah.
Good day.
Quick.